So we described the cyclone as a warm core cyclone, and then we looked at thermal winds. We said the horizontal temperature gradients produce vertical shear. So just describing the cyclones with intensity or location or warm core and cold core is not considered enough in terms of its structure and its evolution in the structure, vertical structure, and the asymmetry, the fronts, and so on. So this method is developed called the cyclone phase space to have a better representation of the storm structure. So this is, I'm just taking a picture from NOAA showing the nice subtropical ridge and how the systems often start as a tropical disturbance, quite often associated with the easterly waves that come off from Africa onto the Atlantic Ocean. Depending on conditions like the vertical shear, available energy from the ocean as hurricane potential, vorticity, moisture loading in the mid-troposphere, vertical motion, and so on. Tropical storm is born, and then it may grow into a hurricane of various intensities, and this is a very general picture. So how do we represent the evolutions? The idea of warm and cold cores is of course associated with the fact that warm core tropical cyclones have the warm tropical air that they pick up, and then the strongest winds are just above the surface. At the surface there's friction, of course, and then as you go up into the troposphere in the cyclone, the winds become anticyclonic, so we have cyclonic converging winds into the eye and the rain bands, as we saw already several times, and that air is then diverging and flowing out of the cyclone as an anticyclone at the top. So that structure, typically here you have like 64 knots near the surface and 34 knots at the outer edge, and you have converging winds shown here. So this warm core cyclones typically are almost symmetrical, and there are no sharp fronts, whereas the extratropical cyclones tend to be what are called cold core, because they have, you can see the cold core temperatures with this tilted structure as opposed to the warm core cyclone here, and they have the strongest winds actually in the upper troposphere, and they have this kind of strong frontal structure that are associated with them, and you can see there is a warm front and a cold front. Often there is what is called an occlusion, so transition can happen from a cold core to a warm core cyclone. The transition of the warm core cyclones into extratropical cyclones is not uncommon, but it's not something that happens all the time. Okay, so you can essentially think of them as tropical and extratropical cyclones with strongest winds in the lower atmosphere for tropical cyclone and the warm core cyclone, whereas the strongest winds are in the upper atmosphere for the cold core cyclone with sharp westward frontal structure. So how does the cyclone phase diagram work? You can see here, sorry the figure is a bit fuzzy in the book itself. I didn't go hunting for it, but anyway, here it is showing on the y-axis the 900 to 600 hectopascal storm relative thickness symmetry, and on this axis it's showing the 900 to 600 hectopascal negative of the thermal wind, which we already defined before. So on the same, for the same phase diagram, this is Katrina and this is Arlene. This is from 2005 and this is from 2005 as well, but this was a remarkably weaker cyclone compared to the Katrina, which of course has now left an indelible mark on what happened to New Orleans, and then all the social upheaval that was associated with it, and how the whole city was changed forever because of this cyclone and the consequences it created in terms of people that got stuck, killed, then so on and so forth. So that's the cyclone structure, and you have various details provided here on the right side, but you can see that the phase diagram of the cyclone Arlene in the lower part is remarkably, so there is Arlene and there is Katrina that made landfall, transitioned into a cold core cyclone, and went out into Canadian waters as a cold core cyclone. So this is a good example of a transition from a warm core to a cold core. But on this phase diagram, you can see this spread on the phase diagram. Both are the same phase diagrams, but you can see that the differences are remarkable. So obviously, just saying the intensity and maximum sustained wind speeds and so on doesn't begin to tell you just how different the two cyclones were. The other part of this cyclone phase diagram is to look at the lower, and so this is the lower 900 hectopascal to 600 hectopascal thermal wind, and this is the upper thermal wind from 600 to 300. And again, you can see that Arlene much weaker and evolved basically around the center of the phase space. So obviously here we have 0, and then the axis here is not on the 0 of the storm relative thickness symmetry, but nonetheless it stays close to the origin, whereas this one covers the phase space much more broadly, and the same thing here. So the lower thermal winds and the upper thermal winds have strong contrasts as it transitioned from the warm core eddy into the, so you can see here clearly warm core to a cold core, so you can see the transition going on from warm core into a cold core eddy, whereas this one basically remained a warm core eddy and maybe slightly touched on becoming cold core as it died away near the Great Lakes, whereas this one went off into the Labrador Sea region, so it had much more power as it continued to go. So cyclone phase space then basically is the idea of having much better representation of the evolution of the structure and transition of the cyclone. Here we are showing diagrams for Tokage, a typhoon in the Pacific here, and a extratropical blizzard of 1993, superstorm of 1993, which didn't get a name. And again, you can see the difference here. This one started as in the thermal wind and symmetry phase space, goes from warm core to cold core, clearly transitioning from the tropics into the extratropics all the way past Japan into almost what this should be Okhotsk, I hope. Gulf of Mexico is on this side, Aleutian Islands are here, so it's headed here into Bering Strait region. And this one originated basically as a cold core in the as a blizzard, and then it wandered around in this phase space and actually eventually became a warm core by what is called an occlusion, where the front, so here, the cold and warm front can get twisted together to transition one to the other. So cold core occluding into the warm core can create a transition where actually you are starting from a cold core, wandering around here, and then eventually becoming a warm core, all the time remaining extratropical. This is the upper and lower thermal wind depiction for Tokage and the superstorm of 1993, again mostly in the cold core space and then transitioning by occlusion into the warm core and then demising into a cold core space again. So this kind of detailed transition is only possible when you do this cyclone phase space, and that's the main idea. This is just the depiction of how occlusions occur. So here you have a cold front running into a warm front, and this is where all the asymmetry and the tilting towards the west and occlusion and so on happen during cyclogenesis in the extratropics, the cold core cyclones. Okay, so that gives us a better sense of the evolution of cyclone instead of just saying the intensity and maximum sustained winds. It's kind of a quick introduction, but you can read up the details if you wish. Okay, I decided to add a couple of more of these cyclone phase space diagrams from Robert Hart's FSU website, just because these figures are so much more clearer than the ones I showed from the Comet book. You can see this is the ECMWF cyclone from 2019, so it has forecasts and analysis here, and the intensity, which we couldn't read before, is shown in terms of the eyewall pressure, and mean radius of 925 hectopascal. Gale force winds are shown here in these scales, but more importantly you can see that in the same way we showed before, storm relative thickness symmetry versus the lower level thermal winds, the phase space here is nicely split into symmetric warm core and asymmetric warm core. Asymmetric cold core and symmetric cold core, and you can see the path here that is shown wandering through, starting from a symmetric cold core here at A, and then going off into the symmetric warm core quickly, and then going on into asymmetric warm core, and then coming back into asymmetric cold core as it transitioned into extratropical cyclone. Okay, so this is much more clear in terms of the phase space and the information that couldn't be seen clearly before. This is the second half of that, where we are looking at the upper level thermal wind, 600 to 300 hectopascal, so 600 to 300. As you know, it goes, pressure drops as you go up, and this is the lower level thermal wind. So here we have deep cold core, shallow cold core, deep warm core, and of course shallow cold core. I hope. So this is again starting here, and as a weak cold core cyclone, transitioning into deep warm core, and then shallow and deep cold core at the end. Over here, and again this is the same information we saw before. So this shows much more clearly why the 3D structure and the evolution of the cyclone is much more clearly depicted in this construct that Robert Hart started in terms of the cyclone phase space. So I hope that kind of adds a little bit more clarity to the previously shown figures. So the other factors remain the same, of course, in terms of the differences between cold core and warm core eddies, cyclones, and the asymmetries and symmetries of the two. Okay.